Thank you. I appreciate the invitation, the opportunity to present. It's always fun to be able to talk a little bit about the work we're doing at OndaVia, some of the things we've done over the years, and we're trying to do, to describe where we see Raman spectroscopy applying. So a little background on OndaVia. Company's 9 years old, when in fact full-time October 1st of 09, so we're just a few days short of having done this for 9 years now. Much of our early work was SBIR government grant funded, so SBIR from National Science Foundation and USDA and NIH. That helped us develop early on, it was environmental applications. We wanted to make laboratory grade water analysis fast and easy. Over the years, we started to get phone calls out of some heavy industry applications, so oil refineries, petrochem, other big industrial facilities, and we use that development as a way to really drive the underlying technology. So to take it from those grants, almost academic level research, and move it to real commercial applications. And now, over the last year or so, we've started to transition back into more environmental applications, more things related to drinking water, and really affecting everyday people. And so it's exciting to talk a little bit about that work and describe what we've been able to accomplish. I'm also the second goal here is to be an evangelist for Raman spectroscopy. It's a technique that's been around for a long time. Many folks may remember one day in an undergrad chemistry course hearing about it, but never have thought about it again. Well, Raman has really developed over the last, I guess, this point, since the turn of the century, has really seen a tremendous growth. And some of the tools we've brought to the table move it into being useful in environmental analysis. So I'm evangelizing a bit for Raman in general. If it's a tool you haven't looked at for a bit, I recommend reading up a little. So let's dig in. Maybe I should start with, if I get my slides to advance here, start with a little bit about Raman spectroscopy. It's not the soup. It is an optical technique named after a scientist that discovered it in the really 1920s, almost 100-year-old technique. It's a spectroscopic method that allows us to observe vibrational rotational modes in a molecule. Right, so you illuminate, you look at a molecule, you illuminate it with light, and you look at the light that comes back, and it tells us information about the structure of those molecules. Up until the 1990s, it was a laboratory-only technique. We're talking about systems the size of kitchen tables, if not larger. High-power, ultra-stable lasers, very sensitive detectors, maybe even liquid nitrogen-cooled detectors, and very, very high-quality optics. So the type of thing that a PhD student would spend the morning adjusting all the mirrors and lenses, take some data, and then do it again after lunch, take some data, and go home for the day. Right? Very difficult to operate. Turn of the century, optical telecom boom, and to do optical telecommunications, we need high power, ultra-stable lasers. We need very high-quality optics that need to perform at 5 nines performance at the bottom of the ocean, and we need really good detectors. All of that turned the components needed for Raman spectroscopy into commodities and enabled portable Raman spectrometers. The picture I show there is a system that's used by law enforcement. It can tell you what's in that Ziploc bag of white powder. Hazmat situations. These systems can roll out in the field, and you can be in the big suit. You can identify a liquid without needing to expose yourself to the liquid with an instrument very quickly and easily. Very commonly used in chemistry to fingerprint and identify materials. A little more about Raman. So in this case, we use a laser to illuminate the sample. Traditional absorption spectroscopies, you might take a broadband light source, you illuminate a sample, and you look at the light that comes back. Some of the light will be absorbed. So some of the photons will go into the molecule, they will excite a bond into an upper state, and then maybe that energy is released as heat or something else, but you see an absorption in the spectrum. If you illuminate the sample with a laser, or with let's say in this case the picture is a blue laser, you're going to see a lot of blue scattered light. That's known as Rayleigh scattering. So a photon goes in, scatters back off that molecule at the same color, the same wavelength, back out. But a few of the photons, a very small number, will get absorbed by the molecule. And they'll come back at a different color. They'll be shifted. So a little bit of the energy will be absorbed by the molecule and be dissipated into another mechanism. That's known as Raman photons. So I love this picture. It's a picture I found online a couple months back. Here we have two vials of material. One is, we're looking at it naked eye, being illuminated with a blue laser. And you can see it looks blue. The light that's scattered out of that looks blue. That's Rayleigh scattering. But if we put a filter in front of that vial, and we eliminate the blue light and just look at the rest of the light coming back, here we see some greenish yellow light that is the Raman light coming back from that sample. In this case, we have a very high power laser, and we have a very strong Raman scatterer, and by eliminating the blue, we get to see with the naked eye the Raman light. Now, much like you might do with absorption spectroscopy, you take a spectrum and you can begin to identify, based on peak location, different bonds within a molecule. So I can look at a Raman spectrum, economic and say, that's probably a phenyl group, and that's probably a carbon-carbon or maybe a carbon-carbon double bond, or I might be looking at some amine activity. Because of the structural information, it's a very useful technique for rapid identification. Plastics recyclers can tell the difference between, a polycarb and a polyethylene type plastic. So here was, a spectrum of mouse bone, right? So able to pick out things like phosphate bonds or carbonate bonds in the bone. So very useful for identification. Now, some of the other useful parts, the principles or I guess benefits of Raman spectroscopy, it works very well with water, because water does not have a very strong Raman spectrum. So we can actually look at materials in an aqueous sample and measure them, observe them, without worrying about a background from the matrix. Unlike an IR absorption spectroscopy, where water will absorb most of the IR. It's also completely optical, so we don't worry about damaging our equipment by putting in a dirty sample. Portable, I showed the instrument earlier. These things can be put in a pocket and go on out and do analysis in the field. And there are many varieties of Raman spectrometers commercially available, so it's a market that's really developed over the last 20 years. But as I said, traditionally used for identification, not quantification. So one more slide here to talk a little difference between Raman and FTIR. They're complementary techniques, right? So one is absorbing, one is scattering. In some cases, the same bond will do the same. Will show up in both techniques. So here I show FTIR and Raman for the same material. You can see a carbon-oxygen double bond, where in FTIR it's strong, but it's weak in the Raman, and then vice versa with a carbon-carbon double. So two techniques that are often very useful together to be able to identify and study materials. So if you've got a lab where you're doing a lot of FTIR, it's worth taking a look at Raman as something that you might be able to add to your toolbox for identification of materials in the field. So spectrometers, the systems that we use at OndaVia, here's two different systems. Benchtop instrument, excellent Raman spectrometer, gives lots of great data, weighs 16 pounds, 12-volt operation. I put in a Pelican case, take it all over the world, do analysis. So relatively affordable, lightweight, easy-to-use system, pretty robust. But true handheld systems are available. Right, so these systems use law enforcement, military, hazmat for identification of materials out in the field. A couple pounds, runs off the USB line. And of course, you can go high-end with systems that do take up a good part of a countertop that will do all types of incredible things. So a wide variety of tools are available in the Raman space, from kitchen table size all the way down to something that if your pocket's big enough, you can fit it. So cool tools, has lots of capability. Why not widely used? Why don't you find Raman spectrometers all over the place? Well, two problems. The first is Raman is a very weak signal. So really good for percent level measurements, bulk measurements, but not really useful for ppm or lower. So environmental analysis, we're typically worried about trace level analysis. And in addition, it's traditionally viewed as an identification technique, but not a quantification technique. So Raman spectroscopy not necessarily Raman spectrometry. In order to address the trace level analysis, we use a technique called surface-enhanced Raman spectroscopy. So this surface enhancement was discovered in the 1970s. Normal Raman is about 1 in 10 million photons come back as a Raman photon. So you have 10 million photons onto a molecule. One of them will come back as a Raman. The rest of them are rarely scattered. But if we do this type of Raman spectroscopy in the presence of a metallic nanoparticle, let's say a gold or silver particle that's smaller than the wavelength of light. In this case, let's say if we're doing near infrared at 785 nanometer laser, we take a particle that's 40 or 80 nanometers in diameter. In this case, when we illuminate that particle, the electrons will start to vibrate. They'll start to move up and down, and we can get a resonance to occur that enhances the electric field at the surface of the particle. This resonance is known as a surface plasmon resonance, and it's really due to the charge of those electrons within that nanoparticle. And what we get is an enhancement to the electric field at the surface of the particle. And what we're really looking at in here with SIRS is an enhancement that occurs within 1 or 2 nanometers of the surface of that particle. And that enhancement can be up to 10 orders of magnitude enhancement to the electric field. And that leads to a very large enhancement in the Raman signal. Now the challenge is it only occurs within 1 or 2 nanometers of the surface of the particle. If you get further away, there's no enhancement, nothing happens. So you need to get an interaction between this metal nanoparticle and what you want to measure. If you get an interaction, and let's say it binds to the particle at the surface, you get a huge enhancement to the Raman response. Now, this has been, as I said, discovered in the 70s, intense academic research over the last 30, 40 years on surface-enhanced Raman spectroscopy. And this gives a better idea of what can happen. If you take a particle, you might get an enhancement that's close. If your analyte doesn't enter that enhanced field, you get no enhancement to the Raman response. But if it does enter that increased field, it can be 10, even 15 orders of magnitude enhancement to the Raman response. And if you were to bring 2 particles together, it forms a little dipole antenna. And now, at that spot between those 2 particles, you get massive field enhancements. Academic research has pushed this down to single molecule detection. These are known as hotspots in the literature, where you can get literally, in some cases that in the academic space, they'll push down to looking at, they can see a single molecule move in and out of a hotspot as they do these measurements. Okay, so now we can take Raman, and for 40 years now, we've known how to enhance the Raman field. Why are we not widely using this? Why is this not a common analytical technique? And the challenge, the Achilles heel of SIRS, has been variations in the response. It's random. There's a stochastic nanoparticle alignments that give those hotspots. So those 2 particles, if we bring them together, not only need to bring them together, but we need to put our analyte of interest in the middle of it. And getting that to be reproducible has been an issue. We actually did a grant application 5, 6, 7 years ago where the reviewers came back and said SIRS doesn't work. And by that they meant it's not reproducible. But what we've done is taken SIRS and really turned it into a reproducible technique, a true quantitative method. And the way we've done that is with internal standards. Not only can we make all of the materials more repeatable, but the true way to make any analytical technique quantitative is to add an internal standard. It's what we do in mass spectroscopy. It's what we do in a variety of other methods. We add a material of a known quantity with a known spectrum that will interact in a way we know, and we reference against that material. And that's how we can do quantification with Raman spectroscopy. So to this day, I still have, I'll do a presentation on Raman, and someone will say, it's a great technique for identification, you can't quantify. What the approach for quantification with Raman is, have a material that's an internal standard, mix your sample with that internal standard, and measure it in the Raman spectrometer. And with the right software, with the right data processing techniques on a computer or within a device, you can then make Raman a quantifiable method, a method for quantification, I should say. And again, it's very quick because really the collection of the Raman spectrum is often a few seconds, maybe a minute or two, depending on the sample. So you can get numbers very, very quickly in a portable instrument. As I said, much of the work we've done has been in the oil and gas sector, or heavy industry. Two materials of interest in that industry have been amines, ethanolamine and methylamine. And here what I show on these histograms are the measurement of ethanolamine and methylamine over the course of 4 years using a single calibration curve. So 4 or 5 years ago, we built a calibration curve using an internal standard of a known quantity. We've then continued to analyze materials over the years. Over 2,000 data points in this set. It's been done over 4 years, 25 different spectrometers, about a dozen different operators, including summer interns that we bring in from local universities, and one calibration curve. And we get numbers that compare with what you would get with ion chromatography. Although, with ion chromatography, you would never bring an intern in from a local university and day one put them in the lab doing, running your system. In this case, because of the simplicity of Raman spectroscopy and the ease of the methods, you're able to do this type of low-level analysis almost immediately when walking into the lab. Okay, let's talk about a few environmental and other applications that hopefully will be a little relevant to the audience. So one of the things we've worked on a bunch recently has been the measurement of chloramines, actually ammonia and chloramines. Chloramation is becoming a popular method and is growing in use for drinking water disinfection. Fewer disinfection byproducts than using chlorine directly. A little bit more of a robust disinfection technique. However, there are some drawbacks and some challenges in terms of process control. Because the way you make chloramine is you mix ammonia and bleach. If the pH is right and you have the right levels, you'll get monochloramine, which is a very effective disinfectant. However, if you get your ratios off a bit, you can end up with dichloramine, trichloramine, and in some cases, if you have a little organic presence, you can end up with organic chloramines in your solution. Those other compounds aren't as good disinfectants, and they can have various other health effects. So being able to measure a chloramine concentration is a very useful tool. But the challenge with SIRS, of course, is we need that interaction between the nanoparticle and the analyte of interest. Chloramine does not naturally like to interact with gold nanoparticles. So we need to do something to get an interaction. And this is where we've looked at techniques that are used in colorimetry. There are colorimetric methods for chloramine, colorimetric methods for a wide variety of compounds. And it turns out that many of those colorimetric dyes are highly SIRS active. Maybe they contain thiols or they contain amines that really like gold. So we can look at colorimetry, use existing methods, existing dyes, existing compounds, and use surface-enhanced Raman as the readout technique. They might say, why do I take a more complicated method to do something that I can just measure with color? The problem with colorimetry, the risks, the drawbacks are you can have interfering compounds. You can often find situations where if there's a turbid sample or it naturally has some color, it's difficult to measure a color change. And we can add internal standards that have a different Raman spectrum even with the colorimetric dye. And that allows us often to improve detection limits and eliminate the impact of interferences. So using a same base principle that you may currently be using in the field, but applying an advanced technique can expand the number of samples that you can measure and increase your confidence in the measurement. So for the measurement of monochloramine, in fact, for the measurement of ammonia in general, the reaction we use is pretty well known. So if you want to make chloramine, you're taking ammonia and you mix it with bleach, and that makes monochloramine. Now, monochloramine likes to will react with phenols. So in this case, this diagram here, we're reacting with a phenol to form a compound. That compound will continue to react with phenol to form a colored compound. This idophenol compound is the yellow, the green compound I showed earlier. Okay? Especially, you can accelerate in the presence of some iron-containing materials to accelerate that reaction. Now, it turns out this colored compound, yes, it's yellow, it's green, it also is very SIRS active. It likes to interact with gold. That nitrogen wants to go to the surface of the gold particle, and those phenyl groups also really like the gold, wants to lay down on the surface of the gold particle and give us a strong SIRS enhancement. So, very SIRS active compound. So, when doing this reaction, we've got two options. If you add bleach, it becomes an ammonia measurement, right? Because then we're converting ammonia to chloramine, and we measure the chloramine. If we don't add bleach, it's a chloramine measurement. For our work, we've moved from phenol to a salicylate because it's a safer compound. Phenol is not all that pleasant to deal with, and salicylate is quite safe. So moving to a different material gives us a little safer and allows us to still do the reaction and still get a nice SIRS response. Of course, we like to use internal standards. That's how we make the method more repeatable and eliminate the impact of interferences. For an internal standard, we use an isotopolog of ammonia. We use a heavy nitrogen version of ammonia. Commercially available, easy to get. By adding a neutron to the nitrogen, by going to N15, we get a shift in the Raman spectrum. So here I show a spectrum, two different spectra you'll see there. The blue is if we have just heavy ammonia in solution, and the red is when we have a mixture of the two. So adding the neutron, we actually get a change in the optical response. Interestingly, they both turn green, and they turn green similarly. So it wouldn't be possible to use heavy ammonia as an internal standard for colorimetry because it's all green. But the Raman spectra are different, and that allows us to then use an internal standard. And really it becomes a self-calibration, right? That we're putting that in there, and now we've built a calibration into our samples. We get, here shows the calibration curve over range of interest, 0 to 15 ppm as nitrogen. This is a chloramine measurement, doing it as chloramine. Again, nice linear curve, nice small variation over that range. And we can do this in tap water, so taking tap water, purging out any chloramine that might be present, and then adding it back in. Again, it works, and this is in the presence of things that might be, potential interferences in tap water, metals, other things that we'd expect in our tap water. And I can tell you we've got a lot of iron in our tap water here in our building, so we know there's stuff in there for sure. And again, we get the same type of measurement, nice linear curve, and we get numbers that respond back as we'd expect. In a few minute measurement using an existing colorimetric method, but using surface enhanced Raman as the readout. Now let's take a little bit of a turn, right? So ammonia, that test works for ammonia, works for chloramine, useful in a wide variety of applications, and it's something that we've been able to take colorimetry and apply it to SIRS in a novel way. But then we can start to step back and say, what else is done colorimetrically? Well, lead, there are colorimetric tests for lead. Lead is obviously a big issue, often is due to corrosion in your pipes inside your house or inside your building. We know, as I said, we know in our office here, there's a lot of iron in our water, likely a lot of corrosion. So something that has been important to us, even with our drinking water here in the office. The challenge with the lead measurements is the colorimetric method is really not that good. It doesn't really have that great of detection limits. If you were to go on Amazon and buy a lead test kit, you can get kits that kind of give you a go, no-go at 15 parts per billion. That's the EPA limit. At 15, it kind of gives you yeah, you've got some or you don't. Not especially quantitative. And, when dealing with lead in your drinking water, you kind of want to know if it's 14 or if it's 25. And much of the easy-to-use kits really can't give you that information. You got to go to the lab and put it through, a couple $100,000 piece of equipment. But we can take that colorimetric method and improve it. So in this case, we use a compound, the image is shown here, that is highly SIRS active when dealing with gold. That molecule not only does it have a ring with a nitrogen in it, it means it's going to like gold, but more importantly, it's got a thiol group, that SH that sticks off there. Those thiol groups will bind to gold almost irreversibly. They love the gold surface. So they will give us a very, very strong SIRS response. And so this spectrum here shows the difference when we have it with and without the presence of lead. So you see a peak that's circled there. The black trace is with no lead present, blue is a small amount, and the red was with a large amount. We zoom in the inset and show the difference between 0, 10, and 30 ppb of lead. All right, so over a range where colorimetry really starts to fail, we get a great dynamic range. We get a very strong response from the SIRS measurement. So using similar compounds that be used for colorimetry or for other techniques, but because of the enhancement and the gold nanoparticle chemistry, we can get a very strong response over a range of interest. And here we show a calibration curve, 0 to 100 ppb, get a wide dynamic range. Great quantification, it's repeatable, works very well. I can zoom in here at the low range where we're really interested, right? And these are the places where you would need to traditionally go to the lab with a very complicated piece of equipment. Here we can do it with an optical method in the field, over 0 to 20 ppb without much of an issue. Of course, the challenge really is in lab standards. Everything's easy when you do it in clean water. But even in tap water, continues to work great. This is our tap water. It contains iron, likely contains some copper, contains some zinc and other things, and we still get the lead to work quite well. When you look at EPA, when you want to measure corrosion in your home piping, you're worried about two things: lead and copper. That's why the lead and copper rule exists. So lead at 15 parts per billion, copper's at 1.3. We can also do copper. In this case, our indicator compound is a material that's used it's a corrosion inhibitor for yellow metals. It likes copper. It also really likes gold. So it gives us a way to bring copper and gold together and get a measurement for copper. Again, this copper is a ppm level measurement, and we get a good calibration curve for ppm level measurement of copper. This is some brand new work that we're just starting to bring on out. But the idea here would be a simple optical methods, be able to do both lead and copper in a couple minute test in remote situations if you want, or even on a kitchen counter if you want to look at home testing. Now, let's take yet another turn and look at some real trace level measurements, some complex samples. Flue gas desulfurization. So a few years ago, we were asked about measuring selenium in the wastewater from coal-fired power plants. Now we don't really have, don't deal much with coal here on the West Coast, but it is a big deal back east. When you burn coal, in fact, any hydrocarbon tends to have a very high sulfur content. So when you burn it, you generate the sulfur dioxide. That leads to acid rain. So coal-fired power plants are required to have scrubbers, and it's often done through a process called flue gas desulfurization. So you can take that sulfur dioxide, convert it to sulfate, and then with a coal-fired power plant, they'll actually then convert that to gypsum. So if you go to Home Depot to buy any wallboard for a home repair project, odds are that the gypsum that you're buying in that wallboard came from the combustion of coal. Now, a massive production of gypsum from that industry. It does a great job reducing the sulfur dioxide, removes a lot of sulfur that would normally go into the atmosphere. The problem is that the wastewater from that process still contains high amounts of not only sulfate, which isn't really a big deal, but other metals: mercury, arsenic, selenium. And then when those end up being, they either end up in fly ash ponds. In fact, the hurricane in North Carolina, there's lots of questions about the leaking from some of those ponds into the rivers. These metals are then present at high levels. And doing a measurement in those samples is very complicated because they're very complex samples. So we've looked at doing sulfate measurement, or selenium measurements at low levels. Challenge with selenium is it doesn't like to interact with gold. In a natural water sample, the selenium will be present as selenate, possibly as selenite, but it's an oxyanion primarily. In fact, same thing with arsenic, arsenite. They have no natural affinity for gold. So if you mix them together with gold nanoparticles, you'll get no enhancement to the Raman spectrum. You'll see nothing. So we look towards things like ion chromatography. We want to get an interaction, so we find things that link the anion with the gold. In this case, I show a picture for perchlorate. So we did work many years ago. In fact, some of our early work was a measurement for perchlorate. It's an oxyanion, much like selenate. We have something that likes to bind to the gold, that's the thiol on one end, and something that's charged on the other end, that likes to interact with the anion. So with these types of techniques, we can then do measurements with the same instrument, same nanoparticles, but adding another material in between that does the linking. We can now do low-level measurements of other materials in solution. For selenium analysis, we're doing, here's the calibration curve over, 0 to a few hundred ppb. Most places, folks are worried about 50 parts per billion environmental applications. I think 50 parts per billion is still the limit on the refineries here in the Bay Area into San Francisco Bay. The new regulations that may or may not occur for coal-fired power plants are looking at going down to 10 or 11 parts per billion for selenium in their wastewater. So very low-level measurements. Currently, you're doing ICP-MS. So very complex tools to be able to measure at that level. With an OndaVia system or with our techniques and the things we've developed, you can really do it with, it can be as quick as a few minutes in a field application. One of the interesting side benefits is the technique we use is very selective for one oxidation state of selenium. It just looks at selenate. So when treating selenium, often the technique is to reduce it, to take it from selenate to selenite and convert it to selenium metal, which precipitates out. By being specific to oxidation state, we can monitor that process as it occurs. So we can do a measurement for selenate, then oxidize the sample, add a little bleach, convert it all to, or a little peroxide, convert it all to selenate, do a second measurement. And that allows us to see the reduction as it occurs. We did some samples that came from, I want to say this was actually a wastewater from a mining facility, where looking at the untreated samples, we were seeing 400 parts per billion of selenate. Everything looked perfect in comparison to ICP-MS. But when we looked at treated samples, we couldn't see anything at all. That's because they had been converted, all of it had been reduced to selenite. When we went back and did an oxidation, we then got all of that selenite back to selenate, and then we got measurements that corresponded to what you would get with ICP-MS. So a speciation test is usually a very complex technique in the lab. Often these things run $300 to have a laboratory test done. And in some of these samples, they're so complex, only a couple labs are really trusted to do it. Here you can do it yourself with a portable instrument in the field. Similarly for arsenic, arsenic exists primarily as arsenite or arsenate in natural waters. 10 parts per billion is your detection limit in drinking water. That's where that's kind of the level you want, but really, I'm not sure you want any. Interestingly, though, the arsenic 3 is more hazardous than arsenic 5. We see the same thing with other things like chrome. Hexchrome is a problem. Chrome 3, not so much. In fact, a little bit of chrome 3 is necessary in your diet, right? So oxidation state is very important. It also affects how you would treat those samples. So just saying you've got some chrome present, just having some arsenic present, isn't as useful of information as knowing which oxidation state does that arsenic exist as. You can do arsenic via colorimetry. You generate arsine gas in the process. It isn't especially pleasant, a little bit hazardous, and then you get no speciation. But using surface enhanced, we can then develop methods that allow us to speciate, build calibration curves for direct measurement of arsenite and measurements of arsenate. And with low detection limits, really with the most accuracy and the most change in signal over the range where colorimetry starts to fall apart. So it gives the ability to apply Raman spectroscopy to true trace level measurements and get additional information that you wouldn't get out of a traditional colorimetric method. I think, zip through that a little bit. Hopefully got a little time for questions here. But, overall, what I wanted to get across today was that Raman spectra is a very powerful tool for analytical chemistry. Been known for a long time, great for chemical identification, law enforcement, hazmat, all types of situations where it gives very quick fingerprinting. But by thinking through the technique, we can take, use tools like surface enhanced Raman and internal standards to convert Raman into a true quantitative method with accuracies and precisions that compete with traditional laboratory methods. With the right tools, these become applicable to environmental analysis. And there are many applications that I'm working that really apply the things we do in California, important here in California. Things like arsenic or nitrate. Nitrate's just an oxyanion that we can measure. Hex chrome and perchlorate, being able to look at hex versus chrome 3, perchlorate in groundwater. Just to name a few, all things that we've played with. If we're interested here, other things that might be coming up out there. If you've got a project in mind or, some type of environmental analysis you want to do, we're interested in working together. Expanding the knowledge base of what's where, time counts in these analyses, things change over time, and building data density, both temporal and spatially, is really important in the environmental side so that we can identify where contaminants are coming from and how best to treat them. So if you have something or some questions, please drop me a note. And I'll switch over to questions here. I do want to give special thanks to our funding agencies. Early on, they did a tremendous amount to really help us bring this technology from almost academic to commercial. And since they are taxpayer-funded programs, I also need to thank all the taxpayers on the line. So appreciate you all listening, and happy to hear any questions you might have.
Thank you for that wonderful presentation. I'm really interested in the miniaturization of technology, making it portable and at low cost, putting it in the hands of community organizations, citizen monitoring, and hopefully we can see adoption of what you presented for those groups that I support through the Clean Water team.
And that's a dream for us too, is that it becomes, the testing becomes pervasive. Right, that it becomes so simple and easy. We just have the data. There's so many other places in life now where you can tweet from the shower, right? So why can't we understand, a little more quickly what's present in various locations? And data density counts.
Mark, are you trying to get the methods approved as standard methods?
That is our goal. It's kind of new technology. It's picking the right places to start and pick the right applications. Our first and foremost, we know that all of our methods need to be as good as the laboratory, if not better, because if it isn't, then it's what is it, right? Where we will likely go first types of approvals will be things like ASTM on some of the industrial side, and then use that as a springboard to then look towards EPA or state level approvals for things like the lead and the arsenic and the selenium. But we need partners there really to drive that forward, because the way you get those approved is you have data, right? And the more samples you put through it, the more confidence you have in the method, the better your data set, and the easier it is to get approved.
Thank you for the question. Thank you for your insightful answer, Mark.